Lecture 1 covers sections 1.2 through 1.5. The scheme within our class will be as follows. Bold words are definitions. Italic words or letters are going to represent variables. Underlined words or phrases represent a law, theorem, and/or hypothesis. Each section, including the number and title, is displayed on the right navigation pane, following our text, and these links are hyperlinked. Important equations will be boxed. At the end of today's lecture, you should be able to understand the concept and formulation of charge and current. You should understand the concept and formulation of voltage. You should recognize and understand active and passive sign conventions. You should be able to understand and apply the formulation of electrical power. And you should be able to understand and apply the conservation of electrical energy. Let us begin by talking about units. The units we will use in this course are as follows. The first column in our table is the quantity. The second column is the name of the unit. The third column is the formula. And the fourth column is the symbol. For instance, time quantifies our unit of seconds, which has a symbol of S. Electric current is expressed as an ampere with symbol A. Frequency, known as hertz, has a formula of seconds to the inverse and has a symbol Hc. Energy or work has the unit joule, which is a Newton meter and expressed by the symbol J. Power is expressed in watts, which is a joule per second, and has the symbol W. Electric charge is a coulomb, an amp second, represented by the symbol C. Electric potential is a volt or a watt per amp, represented by the symbol V. Electric resistance is expressed by ohms, which is a volt per amp, and the symbol is a capital omega. Our electrical conductance is in Siemens, or an amp per volt, with the symbol S. Electric capacitance is a farad, which is a coulomb per volt, expressed by the symbol F. Magnetic flux is a Weber, which is a volt second, expressed by the symbol WB. And inductance is a Henry, which is a Weber per amp, expressed by the symbol H. Now, this course is called Electrical Circuits, and we have to define what an electric circuit is. An electric circuit, or an electric network, is an interconnection of electrical elements that are linked together in a closed path, such that electric current may flow. In the schematic below, we have a Nest thermostat. The top left box is our inductor, where we take 110 volts AC, which is what's powering your house, and we step it down to 24 volts AC. This voltage potential is established across the thermostat, where different switches are able to connect our ground and various other wires, such that we can control various components within our house, i.e. a furnace, a humidifier, or an air conditioner. Now, when we talk about current flowing through an electric network, we first have to quantify what charge is. Charge, represented by the variable Q, which has units of coulombs, which is an amp second, is the quantity of electricity, i.e. the number of electrons that are responsible for an electric phenomena. And mathematically, we express charge as an integral from negative infinity to t of I of d tau. I is our current. Now, we can re-express this integral as Q naught, which is our initial charge within our system, plus the integral from 0 to t of I of d tau. Now, current, represented by the variable I, that has units of amperes, is a time rate of flow of charge past a point. So I is simply the time rate of change of Q. Now, current must be conserved. Charge carriers, which we're going to talk about shortly, cannot be created nor destroyed. So, let's consider an example of the mathematical formulation of charge. Say, for t is less than 0, no charge exists in the terminal of a device. At time t is equal to 0, a 5 amp current begins to flow into the device. We want to determine the charge accumulated for all t greater than 0. And if the current is stopped after 10 seconds, we want to determine how much charge has accumulated. To begin, we'll recall that our charge is equal to initial charge plus the integral from 0 to t of I of d tau. If we have no initial charge within our system, Q of 0 is equal to 0, and this would be the integral from 0 to t of 5 amps d tau. This would be equal to 5 tau evaluated between the bounds of 0 and t. Thus our charge would be 5t coulombs. Now after 10 seconds, we've accumulated 50 coulombs of charge.